I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, for this semester, for this class. Just pray you to help us to end well, just to glorify you, Lord, what we do, Lord. In your name I pray. Amen. So I just wanted to spend a couple minutes before I talk about boring things like the test and the final, and just try to draw some ideas together a little bit and just give you some sense of what's past this point, math-wise. So, we've spent considerable time talking about normed spaces, right? So we talked about, I want to talk to you a little bit about metric space and Hilbert space, just to tell you what those things are, because we're pretty close to understanding those with what we've done. First of all, so we've talked about if you take a vector space, right, and you pair it with an inner product. This is an inner product space, right? So this goes from what? From V cross V either to the reals or to the complexes, right? Depending on whether we're talking about a complex inner product space or a real inner product space, right? And then we also said, well, you can talk about a vector space. And we didn't actually talk about this, but we said that you can use this to define the norm of x to be the square root of xx, right? So we said we can induce a norm. Given an inner product space, we can induce a norm, right? Well, you could be more abstract. You could say, I'm going to take a vector space, I'm going to pair it with a norm. And so, the norm would be a mapping from the vector space to the reals. Actually, you could be a little bit more precise. You could say it's really a mapping from the vector space to 0, infinity. And this norm satisfies 4 axioms. What are the 4 axioms that the norm satisfies? It's already implicit in my definition, but the norm is, I'm doing them out of order actually here. First of all, the norm is non-negative, and the norm of x equals to 0 if and only if x equals. That's usually listed as the last thing, but so I'll do a countdown 4, and then 3. The norm of x plus y is, you proved it, less than or equal to the norm of x plus the norm of y. The reason you could prove it is because you're proving that property for the quote-unquote norm induced from the inner product, right? This triangle inequality. So in the abstract, if you want to talk about a norm, you insist a norm is something that satisfies this triangle inequality. And then what else? Something else, too, I think. The norm of c times x is equal to absolute value c times the norm of x. This should be understood to be either just, absolute value of c is the square root of c squared for the reals, right? If the base field is the reals, it's that. If we're talking about complex numbers, then the modulus of, a plus ib is equal to the square root of a squared plus b squared. This is something, of all the things I've said so far today, this is something that actually matters and you need to fix. A lot of you do not have clear in your mind that the modulus of a complex number is the square root of a squared plus b squared, right? Because I have more than one of you who on the test told me that the modulus of 8 is the square root of 8. Es no bueno. This is not good. This is not true. The modulus of 8 is just 8. Because the modulus of a complex number is just the length of the complex number in the usual Euclidean sense of length. So anyway. Sorry, I'm digressing from my stated goal to say something interesting. Make that go away. And I feel like I'm forgetting something. Let me search the authority on mathematical definitions. Wikipedia. So let's see here. I have somehow, oh, good grief. This is, you see the trouble with the word norm is it has a usage outside of math, right? Like social norms. And that's not the norm we're talking about. All right. come on. Stupid Wikipedia is letting me down. All right, let's try this. Come on. I'm pretty sure that's it, which worries me because I thought there were 4 things. All right, yes.
So Cauchy was on the same list, or the Schwartz was on the same list as
right.
like the triangle inequality.
Yeah.
Is that what you're looking for?
No, the Cauchy-Schwarz inequality is not necessarily part of it. Come on. That's the other thing is there doesn't have to even be an inner product. There are spaces for which norms are defined, and yet no inner product can be defined. In which, in the sense that it can't be defined in the sense that there are norms which cannot be induced from an inner product. In fact, so the notion of a norm is disconnected. It doesn't have to be connected to. Good gracious! I mean, usually, oh, there it is. Finally. Triangle inequality, you can pull the scalar out like that, and then only the 0 has the... okay, so the 4 things, where sometimes this gets separated into 4 things. So anyway, it's all here. It's all here already. This is what a norm is. I know this, but anyway. So for an example, here's an example of a space with a... you're like, well, can you give me an example of a space with a norm which cannot be induced from inner product? Here's the standard example. You can take V equals to R2 and let the norm of, say, x comma y, it can be equal to the absolute value of x plus the absolute value of y. This is the one norm. It's sometimes called the taxicab norm. Do you see why? If you think about 2 points, right? Then what's the distance between those 2 points? I mean, the distance between the 2 points would be what? Distance would be the norm. So the distance from P to Q, now I'm getting ahead of my story. The distance from P to Q would be the norm of P minus Q, or Q minus P, whatever you want. All right. So once we're given a norm, then we can define distance between points by taking the norm of the displacement vector between the points. All right. But this, for example, R2, you can actually prove that you cannot find an inner product that the square root of the inner product of the vector with itself gives you back this norm. It actually is impossible, because it can be shown. So like the reason it's called taxicab, of course, is this is basically that distance, right? I mean, this doesn't make sense in Lynchburg much. So if this is my Q and this is my P, what's my QP? Or PQ? We got what, 8? 2? So like this is absolute value of 8 plus the absolute value of 2, which is of course 10. And the thing about taxicabs is they have to travel streets, and of course you know the streets are always laid out in a north, south, west, east grid, right? So it wouldn't matter if you drove that way or this way, it'd still have the same distance of 10 in the taxicab norm. Again, this example is hard to understand in Lynchburg, where we don't really believe in, you know, perpendicular grids of streets, right? There's like lots of other, there's holes, there's all kinds of topological defects. It's very interesting, actually. But okay, so anyway, a vector space paired with a norm is called a normed linear space. All right, every inner product space is a normed linear space because you can always induce a norm from an inner product, but the converse is not true. Not every normed linear space is an inner product space. So again, inner product space implies normed linear space. All right. But the other way, not generally true. It's often true, though. Most examples, it's true. Often it is the case that you can induce that if you give it a norm, you can build an inner product from it. There is a way that you can do it, but that construction fails for the taxicab norm. Other interesting things to talk about here is the definition of circle. So more generally, you talk about the p norm. So if we have the p norm, this would be the pth root of the sum I equals 1 to n of x sub I to the p power, like that. This is for x in Rn. So you can talk about the p norm on Rn. And you can also talk about the infinity norm, sometimes called the sup norm, which is just the maximum of the absolute values of the components taken. And then it becomes an interesting exercise to look at what the circle, quote unquote, looks like in each one of these notions of norm, this notion of distance. Circle, let's say that a circle is what? Set of points satisfying what? Norm of, let's say, x, y. Well, two-dimensional, okay? So n equals 2. So you can look at the set of norms that satisfies p norm equal to 1 in 2 dimensions, and what do you get? Well, of course, what's the Euclidean norm? That's p equals 2, right? The square root of the sums of squares. That's our usual notion of distance. Okay, so of course p equals 2 just gives me a circle. If you look at p equals 1, you know what it looks like? P equals 1, the circle is actually a diamond. This is p equals 1. If you look at the 3 norm, what it does, if you study the equation, the cube root of the sum of x cubed plus y cubed, if you look at the locus of points that solves that equation, you get something that looks like a bulged out circle. So it looks kind of like this. This is p equals 3. And then finally, p equals infinity. What's that? What are, like, here's some points that are on the sup norm circle. If I need a different marker, perhaps red. So one example of that point would be this point out here, 1, 1. See, the infinity norm of 1, 1 is what? It's the max of 1 and 1. Because the absolute value of the first component is 1, the absolute value of the second component is 1. What's the maximum of 1 and 1? It's 1. So 1, 1 is a point on the sup norm circle, radius 1. And in fact, you get this box. So that's the case of p equals infinity. So, and except for the case of the taxicab norm, I think if I recall correctly, the rest of these can be induced from inner products. I'm not going to show you how. That's really not the point in here. Sometimes philosophers talk about the impossibility of imagining a circle becoming a square. I say they just haven't taken enough math. Because look, a circle is a square, is a diamond, is a bunch of other things. Just depends on your notion of distance, right? If you define distance differently, a square can become a circle. As long as you take as basic the idea that a circle is a set of points that are equal distance from one center point. And that's what all the things I just drew are. There's just different notions of distance. So again, a vector space with a norm is a normed linear space. Now getting back to your question about Cauchy, there's a thing called the Cauchy sequences. What's a Cauchy sequence? I'm not going to give you a technical definition, but basically It's a sequence where the difference of terms gets really small as n goes to infinity. Okay, after I write that sentence out, I guess it just makes more sense to give you the mathematical definition for each epsilon greater than 0. There exists an n in the natural numbers such that whenever n and m are greater than n, that implies that the norm of a sub n minus a sub m is less than epsilon. This is the definition of a Cauchy sequence. A space is said to be complete, all right? A space is said to be complete if every Cauchy sequence converges. So the quintessential example of a space which is not complete would be the rational numbers, all right? So like, for example, v equals to the rational numbers. Can you guys tell me a sequence of rational numbers which converges to something which is not rational? How about the decimal expansion of square root of 2? You've all taken Math 200. Not true. Some of you have taken Math 200. So we could let a sub n be equal to 1.414 blah 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 whatever, and so that could be n, like n digits in the decimal expansion of the square root of 2. For example, a sub 1 would be 1.4. A sub 2 would be 1.441. A sub 3, 1.414. That's about all I remember. But this much I also remember, it's not repeating. Okay? I mean, this goes on and on, in fact. If it did repeat, you could prove that the square root of 2 is rational, but that leads to other contradictions. My point to you is that this is an unending sequence. Is every one of these a rational number? Yep, that's a rational number. That's a rational number. That's a rational number. And yet, as a sub n goes to the square root of 2, as n goes to infinity, right? Is this sequence Cauchy in the rational numbers? Is the difference of a sub n and a sub n getting vanishingly small as you take n and n to infinity? I think you can argue that. I think you can argue that if you take the difference between two decimal expansions of the square root of 2, that you can make that as small as you like if you're willing to go out as far as you like. So yeah, this is a Cauchy sequence, and yet it's not convergent. Because the rules for convergence is you have to converge to inside the space you're in. In the rational numbers, we don't have square root of 2. So this is a sequence which converges outside of the space, which goes to show you, this is, again, not an element of Q right there, right? This is an example of a Cauchy sequence of rational numbers which does not converge to irrational numbers, which speaks to the fact that the rationals are not a complete space. In analysis, you learn there's something that you can do. You can take a space and you can look at the completion. Take a space, form its completion, then that will be a complete space. Basically, you can take the space you're working with if it's got a norm. So the norm is what you need to define sequence, because norm gives you a way of defining when things are close to each other. Right? We need a way of defining how close two elements are to define the notion of sequence. So once we have the notion of how close things are with a norm, then we can talk about whether or not the norm linear space is complete. Right? The rational numbers form a normed linear space which is not complete. But if you take the completion of the rational numbers, then you get a complete space. All right? There's a couple different ways to do that. The standard way to do it, though, gives you the real numbers. The non-standard way to do it gives you something called p-adics. You can ask Dr. Smith about that. I know nothing. But anyway, the real numbers are complete because if you take a Cauchy sequence of real numbers, you get a convergent sequence. And so more generally speaking, if you have a normed linear space which is complete, or in other words, a complete normed linear space, then this is what's called Hilbert space. And I had more fine print over the complex numbers, typically. If in addition, so okay, that's what a Hilbert space is. A normed linear space, though, is just a normed linear space with stripping away the complete. If you just have this much, guys, a vector space paired with a norm, this is sometimes called a normed linear space or NLS, aka a Banach space. Well, I think Banach space. No, I'm still messing it up, guys. Well, curses. No, Banach space is a complete normed NLS. Normed linear space does not assume completeness. If you take this and say normed linear space and the completeness property, then that's what's called a Banach space. I do not assume the Banach space doesn't have to be complex. The complex inner product space, which I think the Hilbert space also has an inner product. That's the thing I'm forgetting. All right. I was getting to a point with all this. And then finally, there's yet another thing you talk about. You're like, oh, yay. In fact, in real analysis, we like to talk about a metric. What's a metric? It's a distance function. It goes from the set across the, from the set across the set to the reals, I suppose. And you have a few different axioms. First of all, it's symmetric. So the distance from x to y is equal to the distance from y to x. It satisfies triangle inequality. So like distance of x to y plus the distance from y to z is less than or equal to the distance from x to z. And what other properties does distance function satisfy? The distance from x to y is non-negative, and the distance from x to x is what? What's the distance from a point to itself? Yeah, 0. Right. And I'm not stating it quite right, though. I mean, the way to state this a little bit more precisely is that the distance from x to y is equal to 0 if and only if what? Yeah, x equals y. So this is the notion of a distance function. So contrast that to inner product and norm. Norm and inner product both involve linearity of the points in the set. Like we've talked about the norm of x plus y. We talked about the inner product of x plus y with z. Right? There was an addition of vectors in the norm and the inner product. So norm and inner product only make sense for vector spaces. Metric, on the other hand, those three properties, they don't assume that you can add points. So you can define a metric on much more fuzzy things, like an open set, like a cloud. You can define a metric on a cloud of points. And there's lots of weirder things you can make metrics. For example, the discrete metric is rather stupid. It says that the distance between, let's see, how's it go? I think if you have here's the definition of discrete metric. This defines a distance function, I think. Oh, I think I have, Does that look like, that looks like a sort of strange triangle inequality, right? Because like, I'm saying that the distance from x to z is, look at this is pretty neat. Like this distance plus that distance is less than or equal to the hypotenuse distance. That doesn't make a lot of sense, does it? This is why analysis is harder. Inequalities are not forgiving, right? Contrast it to the rank nullity theorem, right? Equality, so much nicer. Am I right? No? Too soon? All right. Anyway, my larger point is a metric is something you can define on lots of different spaces, whether they're vector spaces or not. And that's what real analysis is really about, is the study of metrics and their properties. But we spend most of our time on the case that the set is just the real numbers and that the metric is just the absolute value of the difference between points, right? So often the metric can be derived from a norm like this. If you have a normed linear space, you can define a metric by this usual rule that we first learned about in physics, perhaps. But anyway, I just wanted to give you a little window into how we go forward from here. And like most of the time in real analysis, you will spend thinking about issues of metric and also the topology of the real line. So topology basically is the question of what's open. And to say a set is open means that around each point, you can put like a little open ball. Really, if, for example, a two-dimensional space would be open. If around every point you can put a little two-dimensional open ball disk, really, which is inside the set. And if you start thinking about that, and you think about, well, if I can put an open circle around it, I could just well as put an open diamond. I could put an open square. You can pretty easily see that the notion of topology doesn't depend on the choice of norm. And in fact, this is a theorem. No matter what norm you choose for a finite dimensional vector space, you induce the same topology. So anyway, these are the sorts of things I would teach you if I was teaching reals. But hey, I'm not, so you're safe. Let's see here. So I'm just kidding. Real analysis is hard enough as it is. All right, anyway. Well, you can stop record. I'll give you guys your quiz.